Let's take a look at a problem dealing with a damp system. Our problem is going to be this from this picture. A glider on an air track is connected by springs to either end of the track. Both springs have the same constant K, and this glider has mass m. We want to determine the frequency of the oscillation assuming no damping. If K equals 125 newtons per meter and the mass is equal to 215 grams. B, it is observed that after 55 oscillations, the amplitude of the oscillation has dropped to 1/2 of its original value. Estimate the value of gamma using equation 14-16. And C, how long does it take the amplitude to decrease to 1/4 of its initial value? Now here's the interesting thing about this problem. We know that it's damped, but in part A it says to assume no damping. What are we saying? Well, we're saying that the damping constant has to be so small that we can approximate this problem and make it a little bit easier to come up with some equation that gets us close, but it's not going to be exact. But if our gamma value is small, it's really not going to matter. So this is going to be the test to be able to see whether this solution makes sense and whether it is usable. So let's start with what we're given. We know the K of the spring is equal to 125 newtons per meter. We know the mass is equal to 215 grams, which is equal to 0.215 kilograms. For part A, it asks for us to find the frequency. Well, the frequency is just 1 over 2 pi times the square root, and we're just assuming that there's no damping, but we have two springs, so the two springs are going to combine to make the spring constant, the effective spring constant, larger. We'll divide that by the mass, and so we have 2 times 125 newtons per meter over 0.215 kilograms. And we calculate this out, we get 5.427 hertz. For part B, we know that they're asking for the amplitude, but our equation that we would assume for a damped system would look something like this: a times e to the negative gamma t cosine omega prime times t plus phi. But they're only asking for amplitude, and this part, the a e to the negative gamma t, is really the amplitude. The cosine is just oscillating between these two amplitudes as they decay. So this is the only part that I'm interested in. So now it says that I have half of the amplitude after 55 oscillations. Well, 55 oscillations, same thing as saying 55 cycles. And if I multiply that by the period, and the period has the units of seconds per cycle, then that's going to give me some value in seconds, just doing the unit comparisons. So that will give us the time that it takes to get to half the amplitude. So we have 1/2 times A is equal to AE to the negative gamma times the 55 cycles times our period. The amplitudes are going to go away, and the only way I can get rid of the exponential function is to take the natural log of both sides. So natural log of 1/2 is equal to the natural log of e to the negative gamma times 55 cycles times the period. So the natural log and the exponential are going to go away. And that leaves me with negative gamma times 55 cycles times t, the period, on the right hand side. Now I just need to solve for gamma. And that's going to be equal to negative 1 over 55 cycles times my period times the natural log of 1/2. Well, I haven't really calculated the period, but I do know that the period is equal to 1 over the frequency, and the frequency I do know. So let me put this into my equation. Negative f over 55 cycles is, or times the natural log of 1/2. Put in my value. And I get a gamma value of about 0.068 per second. This value is so small that it makes our approximation close. We can use this. For part C, we want to know how long it takes to get to 1/4 of an amplitude. So let's do 1/4 of the amplitude is equal to amplitude E, amplitude times E to the negative gamma times T. And what I'm interested in is T, so I've got to solve for T. The amplitudes go away. I'm going to do the same thing I did before to get rid of the exponential function. Natural log 1/4 is equal to the natural log e to the negative gamma t. And that's just going to leave negative gamma t there, so I can get to t is equal to 1 over negative gamma natural log of 1/4. Put in our values. and that gives me approximately 20.269 seconds.